Hello friends, welcome all of you once again. In last video, we discussed in detail parallel and perpendicular axis theorem. So today we see some other new points in rotational dynamics. So let's start today's video. So friends, today we discuss the different points and these points are, today's first point is angular momentum. Second point is expression for angular momentum in terms of moment of inertia. Third point it is expression for torque in terms of moment of inertia. Next one is the physical significance between linear motion and rotational motion. And last points of today's lecture, it is the conservation of angular momentum. So let's start with the first point, that is angular momentum. Angular momentum, or simply it is called as moment of linear momentum. The quantity in rotational mechanics analogous means similar to the linear momentum. It is called as the angular momentum or moment of linear momentum. It is similar to the torque being moment of a force. If P is the linear momentum of a particle undertaking a circular motion, its angular momentum at that instance is, we know the relation, that is L vector is equals to R vector cross P vector, where R vector it is called as the position vector from the axis of rotation. In terms of magnitude, it is the product of linear momentum and its perpendicular distance from the axis of rotation. So in terms of magnitude, this relation can be written as L is equals to P cross R into the sine of the theta, where theta is smaller angle between the directions of P vector and R vector. Let's see the second points of today's lecture, that is expressions for angular momentum in terms of moment of inertia. Let's see the diagram. First we see the explanation of this diagram. Here consider a rigid object rotating with constant angular speed omega about an axis perpendicular to the plane of the paper. The object consisting of n number of particles having the masses, first particle having mass m1, second particle having mass m2, there are large number of particles, that is masses m1, m2 up to the mn. At perpendicular distances, that is for the first particle perpendicular distance from the axis of rotation, it is the r1. For second particle perpendicular distance from the axis of rotation, it is the r2. So at perpendicular distances, that is r1, r2 up to the rn from the axis of rotation. As object rotates, all these particles performs uniform circular motion with the same angular speed but with different linear speeds. We know very well the formula for the linear speed, that is V is equals to R into the omega. So for the first particle, relation is V1 is equals to R1 into the omega. For second particle is V2 is equals to R2 into the omega. There are large number of particles, so the last particle having the linear speed Vn is equals to Rn times omega. So we have to calculate linear momentum of the first particle. We know that the formula for momentum, that is mass into the velocity. For the first particle, the equation being P1 is equals to M1 into the V1. So we know that the V1 relation, that is V1 is equals to R1 times omega. So putting this value in the equation, we get the new relation, that is P1 is equals to M1 R1 into the omega. From this, we calculate the angular momentum of the first particle. Angular momentum relation, it is L is equals to P into the R. So for the first particle, L1 is equals to P1 into the R1. So putting the values of the P1, that is M1 R1 omega in this relation, we get the new expression L1 is equals to M1 R1 square into the omega. For second particle, it is L2 is equals to M2 R2 square omega. For third particle, it is similarly M3 R3 square into the omega. There are large number of particles, so we get the final relation. It is Ln is equals to Mn Rn square into the omega. For a rigid body with fixed axis of rotation, all these angular momenta are directed along the axis of rotation. So, as all of them have the same direction, but their magnitudes can be added. So, we get the new relation, that is L is equals to, adding these quantities, we get L is equals to M1 R1 square omega plus M2 R2 square omega up to the Mn Rn square omega. So, simplifying this relation, we get L is equals to, into the bracket, simplifying this, that means M1 R1 square omega plus M2 R2 square omega up to the Mn Rn square, outside the bracket, that is omega. So as we know that I is equals to, that means moment of inertia is equals to M1 R1 square plus M2 R2 square up to the Mn Rn square. So simplifying this relation, we get L is equals to I into the omega. This is the expression for angular momentum in terms of the moment of inertia. Let's see the new expression. Expression for torque in terms of moment of inertia. See the figure. Here also a rigid body rotating with constant angular acceleration alpha about an axis perpendicular to the plane of the paper. Here also object consisting of n number of particles having the masses, first particle having mass m1, second particle having mass m2, and up to the last particle mass, it is mn. Similarly, at perpendicular distances, that is from R1, R2 up to the Rn from the axis of rotation. Here also, as object rotates, all these particles perform uniform circular motion with the same angular acceleration alpha, but with different linear acceleration. So we know that the formula for acceleration, that is A is equals to R into the alpha. For first particle, equation becomes A1 is equals to R1 times of alpha. For second particles, it is A2 is equals to R2 times of the alpha. For n number of particles, An is equals to Rn times alpha. From this, the force experienced by the first particle, we know that the formula for the force, that is force is equals to mass into the acceleration. For the first particle, F1 is equals to M1 into the A1. So putting the values, that is R1 into the alpha in this equation, we get the new expression F1 is equals to M1 R1 times alpha. From this, we calculate the torque experienced by the particle. For the first particle, we know that the expression for the torque, that is tau is equals to F into the R. For the first particle, that becomes tau1 is equals to F1 times R1. So putting the values of the F1 in this equation, we get into the bracket M1 R1 alpha outside the bracket, that is r1. Simplifying this, we get m1 r1 square alpha. For second particle, tau2 is equals to m2 r2 square alpha. Similarly, for the third particle, it is tau3 is equals to m3 r3 square into the alpha. There are large number of particles, so we get the relation tau n is equals to mn rn square alpha. If the rotation is restricted to a single plane, the directions of all these torques are the same and along the axis. So resultant torque we have to calculate, that is addition of all these. So we get the relation, that is tau is equals to tau1 plus tau2 up to the tau n. So putting this value in equation, we get tau is equals to m1 r1 square alpha plus m2 r2 square alpha up to the mn rn square into the alpha. Simplifying this equation, we get tau is equals to into the bracket m1 r1 square plus m2 r2 square up to the mn rn square, outside the bracket, that is alpha. Here also we know that moment of inertia, that means I is equals to m1 r1 square plus m2 r2 square up to the mn rn square. So we get the relation in simplified form, tau is equals to I into the alpha. So this is the expression for torque in terms of the moment of inertia. So let's see the next point of the lecture, that is the physical significance between linear motion and rotational motion. Let's see the first point. In linear motion, linear momentum can be expressed as, we know that P is equals to mass into the velocity. In rotational motion, that becomes angular momentum. Relation it is L is equals to I into the omega. So here friends, moment of inertia replaces by the mass of the particle. Second, we know that in linear motion, force is equals to mass into the acceleration. In rotational motion, here called as the torque, tau is equals to I into the alpha. So here also moment of inertia is replaced by the mass of the particle. So it is the very important physical significance in linear motion and rotational motion. Let's see the next point. Next point is the conservation of angular momentum. In last 11 standard, the linear momentum, we see that the linear momentum of an isolated system is conserved in the absence of an external unbalanced force. So we know that torque and angular momentum are the respective analogous, that means similar quantities to the force and linear momentum. Angular momentum or the moment of linear momentum can be expressed as, in terms of vector form, that is L vector is equals to R vector cross P vector. We know that R vector, it is the position vector from the axis of rotation, and P vector, it is the linear momentum. From this we calculate some derivations, some mathematical steps. We know that the equation L vector is equals to R vector cross P vector. Differentiating this equation with respect to time, we get the equation dl vector by dt is equals to simply d dt of R vector cross P vector. So here applying the mathematical or differentiation rule to this equation, we get the new form dl vector by dt is equals to R vector cross dp vector by dt plus dr vector by dt cross P vector. We know that is force means rate of change of linear momentum. So the equation that becomes dp vector by dt is equals to f vector and dr vector by dt is equals to v vector. So putting this value in the equation, we get the relation that becomes dl vector by dt is equals to r vector cross f vector plus v vector cross p vector. We know that P becomes the momentum, that is the formula mass into the velocity. Putting this value and simplifying this equation, we get dl vector by dt is equals to r vector cross f vector plus m into the bracket v vector cross v vector. So we know that self cross product is 0, that means becomes v vector cross v vector is equals to 0. So putting this value and simplifying this equation, we get the relation, that is dl vector by dt is equals to r vector cross f vector. We know the relation dl vector by dt is equals to r vector cross f vector. But we know that r vector cross f vector, it is the moment of the force, or simply we called as the torque tau. So we get the relation, that is dl vector by dt is equals to simply tau vector. Here thus if tau is 0, we know that dl by dt, putting the value in the equation, we know that dl vector by dt is equals to simply 0, or we get the relation, that is L vector is equals to simply constant. Hence the angular momentum is conserved in the absence of external unbalanced torque. This is the principle of conservation of angular momentum, analogous, that means similar to the conservation of the linear momentum. So friends, today we see the different mathematical expression in detail. In the next video, we see the remaining points of this topic.